Okay, let's get started. So just an administrative note, we have a TA assigned to the class now. Her name is Ching Sun. She's my PhD student. She works in the general area of probabilistic graphical models or for computer vision problems like image segmentation. So now that we have a TA, I mean, she's working on your homework 0 grading now, so we should know soon. We're going to post her office hours on the website, so if you have any questions or anything, feel free to get in touch with her. I should know this, she's in the third year. She's dealing with machine learning on a day-to-day basis, so feel free to get in touch. Okay, so here's where we were last time. We presented you with a general picture. This was the general picture of supervised learning. There's an unknown target function. You don't know what that is. You're given a set of training examples, x1, y1 through xn, yn. That's a data set that you're given. Your goal, the way we are formulating, so your goal is to make predictions about that unknown target function on new x that you have never seen before. And the way you're going to do it is, we're going to come up with some set of mappings from x to y. That's the hypothesis set, that's our model, that's a model class. And we're going to write down an algorithm that searches in that set. So it finds one particular mapping that does not only well on this training data given to us, but also on new data that we will see in future. Okay? And we didn't tell you how do you pick this and how do you pick this, and that's where all the design choices lie. And the algorithm that we were looking at last time, the nearest neighbor algorithm, actually doesn't do any of this. I didn't tell you what a hypothesis class in that case was. I didn't tell you what the learning algorithm was because there was no learning algorithm. What it was doing was it was just storing all data, and in order to make predictions, it was just looking at how have I seen similar ones. So I think we showed you this last time. You're given some data set. This is a two-dimensional space. We can come in and query at any new point. So the red point is new, and what you're going to do is, in this case, you're going to find the one nearest neighbor, in which this is the blue point. You can search for a higher number of neighbors. In this case, you're finding a distance ball with sort of 3 nearest neighbors inside that, and you're looking at their labels. In this sort of description, I'm not showing you the labels associated with these data points, but you can imagine that it is clear that there is some sort of separation going on. There's a bunch of data here, and there's a bunch of data here. If you query in between, then I find some neighbors on this side, some neighbors on this side, and I can imagine that if I look at the proportion of the labels associated with those two, I can get some sense of confidence. Like if this was class 1 and this is class 2, right now this data point has 2 neighbors that are class 2 and 1 neighbor that is class 1, so your confidence is far lower. If you query a point here, all your neighbors are coming from that class 1, so your confidence is much higher. Okay? Alright, so that's where we were last time. Okay. And this idea of confidence ends up being quite useful. If you can measure how many of your neighbors, then it sort of gets you some sort of confidence. So today what we're going to do is, that was our last time. What we'd like to do today is, I'd like to expand a bit more on our discussion about loss functions and how do we measure performance. So now that I've presented a sort of trivial algorithm to you, I can sort of break down how do you know how well it's doing. We looked at that last time, but I'd like to expand on one particular thing today. And then we look at a few design choices associated with nearest neighbors. We look at what are the common distance metrics, and how do you look at some other types of nearest neighbor algorithms like kernel classification. Okay, so let's do this. Let's do this on the board. So last time I introduced something called a loss function or an error function, and we said this is what tells us how well we're doing. There is ground truth in our training data set. This is the prediction that we make, and this is the this is how we measure how well we're doing. Whether it can be 0, 1 or something on classification. This was on a single point. The way you would measure this, so for example, for classification, it can be 1 if y hat not equal to IGT, and 0 else. If you predict the same thing, then there's not an error. And what you do on an entire data set is that you would go ahead and you'd sort of loss or error on data set D, you would sort of go ahead and divide by n and compute the average of n of y or y hat. Right? So just count the number of mistakes you're making on the entire data set, divide by the size of the data. So that's the average sort of error, misclassification error, if you will. So here's a thought experiment. You're trying to classify, you're given a data set of, let's say, medical diagnosis of patients, and you have to predict whether they have cancer or not, right? So it's a binary classification problem, +1 cancer, 0 not cancer. You run an algorithm, and the result that comes back is that your accuracy is 99%, and your loss or your error is 1%. Right? Is this good?
Depends on the 1%.
Depends on the 1%. Okay, so at least we're thinking. So this is great. The number 99% sounds really good. But what if you open up the data set and it turns out that the distribution or the percentage of y I labeled as +1 was only 0.5% in the entire data set. And 99.5% of the data was negative, because most people don't have cancer. Okay? Now does that look good?
Still we don't know.
Still we don't know. So why does that not look good?
If the 1% is all they have, then the problem.
Not bad, not bad. Okay, so that's a good intuition, and what he's getting to is I can write a dumb algorithm that can do really, really well on this data set. And here's my dumb algorithm. Y hat of x is equal to 0 for all x. No matter what your input is, just predict nobody has cancer. How well does that do? 99.5%. That's a problem. So this is what comes up when you have skewed distributions of classes. This happens a lot because usually the quantity you're interested in estimating or predicting, there's some category that some event or something that you're interested in finding, and that happens to be rare. And that is what usually in binary classification problems you'll call it +1. And if there's a lot of skew, just predicting that never happens does really well. Right? If you just measure in terms of misclassification. So we're going to have to do a little bit smarter. We're going to have to write down the kinds of, and that's sort of where he was getting to, we're going to have to write down the kinds of mistakes that we're making. Okay? This algorithm is making a particular kind of mistake, and we'd like to expose that. Okay, so instead of this loss, the thing that we're interested in is the thing that we were drawing last time. We're interested in the confusion matrix. We'd like to know what are the true positives. YGT. Is that visible in the back? Can you see that right now? Okay. So there's you predict 0, 1. The ground rule is 0, 1. You said this was true positives. This was true negatives. This was false positives because you predicted a positive and it wasn't. This is a false negative. You predicted a negative and it wasn't. Okay? These are the correct classifications, and these are incorrect classifications. Those are your mistakes. Okay? And the thing that this single number wasn't really telling us how to compare these two algorithms. One that I implemented and one that doesn't really do anything. And what we'd like to do is expose them in terms of two other quantities. So, okay. So what we'll do is we'll write down something called the true positive rate. And that's, make sure I don't make a mistake in this. That's your number of true positives divided by. So actually, one thing that I want to mention is, if you look at this table, if you do this over the entire data set, you count how many true positives you're making, you count how many true negatives you're making. If you sum up the rows, they're telling you how many positives and negatives happen in the ground truth. They're telling you the distribution of categories. So, ground truth labeled 1, it can be labeled 0 or 1 by your algorithm. So if you sum up the rows, that's telling you, this thing is the number of positives in ground truth, where ground truth is the training data or the annotations that are provided to you. Right? Is that clear? Why the sum of this row is equal to the positives? Because they're labeled positive in the training data. You can either predict them as 0 or 1, you sum them, those are only two cases. Okay? And similarly, if you sum up this row, that's the number of negatives in the. Okay. And we were trying to get to this last time, that you want to somehow look at, you want to normalize the rows. Why do you want to normalize the rows? Because there may be far fewer positives than the number of negatives. And that's what this number that we were trying to get to, this is called true positive rate. And that's number of true positives divided by number of positives in the ground truth, where GT stands for ground truth, or the annotation is provided. This is essentially telling you, in this data set, there were that many people who had, let's say, cancer. How many did you find? What percentage of cancer patients did you actually identify? Okay. Positives, if that is the cancer. So it should be clear that we want this number to be high. We'd like this to be as close to 1. And that algorithm was not, we'll talk about it, but that dumb one was not doing a good job at this. The other number that we'd like to study is the false positive rate. How frequently do you make mistakes? And that's number of false positives divided by number of negatives in ground. Okay. So if I give you 100 normal patients that don't have cancer, how frequently are you going to predict that they have cancer? Which is a problem. That's a mistake that you're making. Okay? And it should be clear that we want this to be a low number. Does that make sense? The true positive rate is sitting here in the matrix after normalizing. The false positive rate is sitting here in the matrix after normalizing. In fact, I can write this out a little more explicitly, in the sense that I can say, this is just number of true positives divided by number of true positives plus, I need the positives, true positive, false negative, plus number of false negative. Okay? So the mechanical view is that you go ahead, you make predictions on a data set, you count what type of mistakes you're making. Are you getting this correct, wrong? And then you compute this ratio, and that tells you your true positive. And you can fill in a similar number. So number of false positives divided by number of false positives plus true negative. Okay. I'm just, sum of this row and the sum of this row. That's what I'm writing here. Okay, so far so good. Now let's take, in particular, so not just that dumb algorithm, but let's take one other dumb algorithm. So this algorithm says nobody has cancer. Right? The world is rosy and lovely, nobody has cancer. There's another algorithm, y hat x equals 1. Everybody has cancer. Okay? And there's a third algorithm that says flip a coin and just start, just flip a coin. Y hat of x is equal to is 1 if heads, otherwise tails. Which means that you just come up with a random number And if your random number is greater than 0.5, where R is a random number, then you call that they have cancer. There's a 3 dumb algorithms and they behave extremely differently in terms of this. So the first one, anybody want to tell me what is false positives and false positive rate and true positive rate for the one that says nobody has cancer?
True positive rate 0.
True positive rate 0. Why?
We didn't catch any true positive.
You're not making any predictions. Nobody has cancer. So how can you possibly get anything right? There are some people who have cancer. And assuming that your data set, your denominator is not 0, right? This is going to be always 0. False positive rate.
We have 0 false positive.
1 minus 0. 1 minus 0? 0.
0 also. Huh?
No, but there are no. So it's counting the number of false positives. You said nobody has cancer. How could you get anything right? I mean, or in this case, how could you get anything wrong? Right? We're only counting out of the people who did not have cancer. You're not going to make any mistakes because you're just not saying anybody has cancer. Okay, so we can get 0 false positive and 0 true positive and 0 false positive. Let me put the arrows back. We'd like this number to be high and this number to be low. Okay, we'd like to have, what is ideal?
1 0.
1 and 0. We'd like to catch 100% of the cancer patients and not make any mistakes on the non-cancer patients. How about this guy that says everybody has cancer? Anybody want to give me the number?
Gonna be 1.
1, of course. You catch all the cancers. You catch everybody who walks through your door who has cancer is lucky on that day because you catch it. What about somebody who doesn't have cancer?
Also 1.
Also 1. Unfortunately, everybody who does not have cancer also gets, you make a mistake there. 1 1. How about the random? This one's slightly trickier. So somebody walks through your door, you flip a coin. If it's heads, they have cancer. If it's tails, they don't. So what is this ratio? That's an infinite people walk through your door. What is this? And you can process them in an extremely small time. What is this ratio going to? It's an unbiased coin, and that's why it's 0.5. So we're talking about the number of people who actually have cancer. Half of them you're going to catch because you're just flipping a coin. And the ones who don't have cancer, half of them you're going to make a mistake. Okay. So this is telling you a little bit of teasing apart what that one number, 100% or so, or 99% was doing into these 2 different numbers. And there's a trade-off between the 2. If you just if you just told me don't make any mistakes, I can do that really easily. Right? Here's no mistakes. I just won't make any mistakes. If you told me catch all the cancers, I can do that also really easily. It's the thing trying to do them together that's problematic. Right? Okay. By the way, just for sake of completeness, just to point out that the accuracy metric, which is sort of 1 minus misclassification that I was writing. Peng, is that visible? Can you see that over people's heads? Yeah. Okay. So the accuracy metric, the 99% that we were computing, is just number of true positives plus number of true negatives divided by size of data set. Which is, in this case, all 4 of these numbers. True positives, false positives, false negatives. All 4 of the numbers here summed up to the size of your tables. Okay? So it's related to these 2, but you've sort of teased out the ratio in 2 different things. Okay. And this should tell you the fact that we're measuring performance along 2 different measurements, 2 different axes, should tell you that at some point we have to run into a sort of a plot, a curve of some point. So let's make that up. So which one should I raise? Okay. We can make a curve on the x-axis. We can plot the false positive rate, and those are the mistakes. We'd like those to be small. On the y-axis, we can have true positive rate. That's accuracy. That's good. We'd like that to be high. This starts at 0, 0, ends at 1, 1. We said, okay, 1, 1 is the performance of the thing that calls everything as positive. So this point is achievable really easily. Just call y hat equals 1. This point is achievable really easily. Y hat equals 0. This point is also achievable somewhat easily. Just flip a random coin. Right? It's this point that's hard. That's where we'd like to be. This is 1, 0. And in fact, what we'll find is if you often the way we're going to report results is we're going to make a plot in this space. What we're going to do is we're going to say that your prediction y hat is actually equal to, so you take sine or your threshold, basically some score that you're computing at x, and you'll check against a threshold. Right? So you'll compute a score or a confidence, and you'll check against the threshold. And the confidence comes from various things. We'll look at probabilistic classifiers later on. We haven't talked about that yet. If we talk about nearest neighbor, we talked about the ratio of positives to the k neighbors. And how frequently do I see neighbors of one class in my k nearest neighbors? If that is greater than some confidence, I'll say +1. Otherwise, I'll say -1. So it should be clear what happens as we vary t. If I set t, if my score or confidence is going from 0 to 1, let's make that simple assumption that they're going from 0 to 1. If I set my threshold to 0, I start calling everything as positive. Right? Because if my scores are always positive, if my threshold t is 0, then I call everything positive. I'm operating here basically. If I set my threshold too high, to 1, nothing gets called positive because my scores are between a range of 0 to 1. Right? So I start operating here at this point. I call everything 0. And basically what happens is as you vary your threshold from 0 to 1, you end up tracing out a curve. Every single point on this curve corresponds to one particular threshold. Notice nothing has changed about your algorithm or your implementation. Your algorithm is still producing a confidence or a number, and you're plotting its performance in this space with a curve by varying the threshold. Does that make sense? And a perfect classifier sort of goes immediately, jumps, it's a discontinuous thing, its performance is like this. Because a perfect classifier is always confident about the actual positives and gives a score of 0 to the actual negatives. So as soon as you make the threshold slightly higher than 0, you end up, you get everything right, and then you're just changing this thing. Does that make sense? Okay. Interestingly, there's going to be this particular diagonal line that is going to play a really nice role here. If instead of actually flipping a coin, if you come up with a confidence, which is just a uniformly distributed random number, and you check against the threshold, you trace out this particular line. Basically, you're making the same ratio of mistakes. You're not looking at the data, but how many, what your true positive, false positive rate is varies based on that threshold. That makes sense? So this line ends up being chance or random. If you don't look at the data, here's how well you'll perform. If you just flip a coin and make a decision, and that line is the performance of your method. That makes sense. So, here's a bad classifier, and here's a better classifier. As you get closer and closer to the upper left corner, that's a good one. As you get closer to random, that's a bad one. Pop quiz. How about this one? Is this a bad classifier or a good classifier?
Brand bad, but you can make it good by flipping.
It's a bad classifier, but you can make it good by flipping. What's happening is that, it seems to be performing worse than chance. What's happening is that, you're picking a threshold, and it's, most of you're still making a lot of mistakes at that threshold. What's happening is that it's giving high score to all the negative ones and low score to all the positive ones. And somewhere in your code, a bug has been made where +1 got swapped with -1. And so this is what that usually looks like. If you're operating lower than chance, that's great. There's still a signal. It's a bug, we know how to solve that. If you're performing really close to chance, that's a problem. That we don't know. That's a much harder thing to solve. Okay? Okay. So let me bring the display back. And let's see if I can. Okay. All right. This is a really nice example of sort of. Okay, so forget all the text, because it was made by people who weren't following my example. I'm actually just borrowing theirs. So let's say you're trying to do a binary classification problem, and on the x-axis, you'd like to classify people based on their height into genders, men or women. Okay, so you just measure one dimension x, and this is y. And the two bell curves are, most men, in the US at least, let's say their average height is like 6 foot. Oh, and most women, I guess their average height is 5'8" or 5'10", whatever. Make up some numbers. And what we're looking at is the distribution of the data. You can think of these as extremely fine histograms if you're not comfortable with PDFs. If you are, then you know what this is. Okay. So we're on the x-axis is height. On the y-axis is the density or the percentage. And this curve corresponds to men. This curve corresponds to women. And what we do is. That's our single feature, that's x. We just check against the threshold. If you're greater than this threshold, we predict male, otherwise we predict female. Okay? Let's see. And there is the ROC curve. There is the curve that we just plot. I didn't actually say that was an ROC curve. And what we're going to do is, you can see that so here's a really high threshold. This is the threshold line. Everything greater than this, so this blue shaded region, you're getting correctly, right? These are the only men that you're actually calling men. Everything less than this, you're calling women. So you get a whole bunch of these people. If this was a histogram, if you think about it, if you just sum up these people, you're getting them wrong, and these people you're getting all right. And so if in the 2 by 2 table, you get a 2 by 2 table, no, not a 2 by 2 table. Okay, but you get you have an extremely high threshold you're operating here. As you sort of lower your threshold, you start your false alarms, so your false positive rates start going up, and at least your accuracy, your true positive rate also starts going up, because as you lower your threshold, you get more of the men correct, but you start now, as you lower your threshold, you start making a mistake on some of these women. So this shaded region right here are the women who are greater than your threshold, where now your classifier is calling men, right? And so that you're making a mistake there. And so this is the point that we're operating at, and you keep lowering that threshold, and you carve out this particular curve exactly. Okay? Makes sense? The threshold here is going from 0 to 7 or whatever. That's sort of, the scales aren't normalized. But in practice, you would sort of scale things, and this is where you'd like to operate. One thing I should mention is, here's another thing that we can play. Let's say the data came to you. This is a well-separated, this is an easy classification problem, right? That threshold, I can find a really nice threshold operating region where I perfectly separate the one class from another class. Right? And this is a harder classification problem because the feature I'm measuring and the threshold that I'm computing on, there's so much overlap that, at this point, I get these people wrong, I get these people wrong, I get this shaded region right and this region right, where I'm sort of operating here. And you can tell in the shape of the ROC curve. If you look at the shape of this curve, you'll find that as the histograms become more and or the distributions become more and more overlapping, your problem is essentially falling to random. You cannot do better than random chance, right? You have this, no matter where you place the threshold, you're going to get, for every person that you get right, you also get one person wrong. Make sense? Okay. And if it's an easy problem, suddenly your curve starts looking like a box shape. That's ideal. Okay. All right. This curve is known as an ROC curve or a receiver operating characteristic. Comes from really old notation. Second World War. This was a bunch of radio people were trying to do something. We don't really care, but it serves our purpose. Okay, so we got that right. So one thing that I mentioned that in terms of this curve, often we talked about close to being chance or being boxy shape. One performance metric that people often use is how well are you doing? Well, let me just take whatever curve you're producing and let me look at the area under the curve. And so if the area under your curve is large, you're probably closer to this point. If the area under your curve is close to half of 1 times 1, in which case half, then that you're close to chance. So even if you have skewed distribution of categories, you can sort of 0.5 chance, it's sort of nice. Everything is sort of scaled up. That makes sense?
So
Yes.
the shape of curve is only a function of the data set?
The shape of the curve is a function of how easy the data set is, how strong your classifier is, like how well you're doing, basically. You could be doing well because the problem is easy or because you're smart. Right? Or both. All right. Okay, so let's actually one last thing about this. This is a curve that plots true positive rate against a false positive rate. One of them is mistake, one of them is accuracy, or a measure of goodness. There is another curve that is often used, which is called precision recall curve. Precision recall curve. It's extremely similar concept. Recall is on the x-axis, precision on the y-axis. Incidentally, in both of those are sort of measures of how well you're doing. So, perfect classifier in that case doesn't lie at 1, 0. It actually lies at 1, 1. But a lot of the ideas go through. I've put in pointers of where to read that, but it's sort of we'd like to move on because everything that we discussed here sort of generalized. Okay. So now let's move to nearest neighbor. Let's do a little more digging. So last time we introduced nearest neighbors, we said, okay, if you answer these 4 questions, you can come up with a family of algorithms, which would all be sort of instance-based algorithms, which is I have a training data set. I don't actually learn a model. What I do is at test time, you tell me what distance metric you're using. I'll find the nearest. I'll find 1 or k neighbors, and I'll use them to predict the output at the test function. So this is 1 nearest neighbor, and the answers here are Euclidean distance, one nearest neighbor, and there's no need for weighting, and just predict the same output. If you're doing k, you would sort of do an average instead. So today what we'd like to do is we'd like to get a little bit into detail of what sort of distances and what effect does that have. Okay? So let's get active on that. A little bit of notation. So here's what we're going to be doing. We're going to use n of x, n of q, right? That's what yes. So we're going to use we're going to say n of k of x is the set of indices of k nearest neighbors of x in the data set. Okay? Just it'll make the, we talked about this at a high level. I said, go find k nearest neighbors. Now we'd like to sort of write that mathematically. So you come up with a bunch of indices of the k nearest neighbors. If you're doing regression, you can do k nearest neighbor regression by saying y hat of x. Just predict the unweighted average value yi in this set. Right? So a nice fancy math way of saying go find the k nearest neighbors, take their regression values yi and just take the unweighted average. Okay? That makes sense? But I'm defining this because later on I'm going to generalize this and it'll help if the easy stuff is clear. All right, if you're doing classification, then you'll say y hat of x is equal to argmax over category C of summation indicator yi equals C, where I is the next k of x. Okay. So this is an indicator function. What I'm doing is the ith data point labeled with category C? If so, sum it up, and I'm just taking an argmax over C. So just find me. So this is counting basically number of yi's that are labeled C. This is just counting, and this is giving me a sense of confidence, and I'm just taking the argmax of that. Fancy way of saying majority weight, right? And I'm going to. This is all unweighted. I'm going to generalize this later.
Excuse me.
Yes.
What was the I for?
What was the I for? So the I is a data
No,
point.
the other one.
The integrated.
Oh, the capital I.
Yeah.
Sorry, indicator. So is yi labeled with C or no? Sorry. This is just this is +1 if yi equal to C, and it's 0 if yi not equal to C. It's just an indicator. But thank you. This is great. I mean, this may not be a standard notation. Okay. So we're just counting. All right. So that's your classifier. That's your regressor. Okay. So the key. So these seem pretty straightforward. This is not hard. The key thing seems to be how do we find these neighbors? And we said, we'll have to define some sort of distance. So let's look at a couple of distances that we would use. Actually, show a picture first. Okay, this is sort of one nearest neighbor for regression, if you will. There's an x-axis, that's your data. This is the data that you have seen. So we talked. Let's assume on the x-axis is the square footage of your house, and the y-axis is, let's say, price. This is not a good curve. It's not going up very fast. But this is a one nearest neighbor fitting because you start at x. At this point, you query who's my nearest neighbor. This is the nearest neighbor, so that's your function. And this is sort of a bumpy function, right? Okay. As last time, let's take a couple of minutes. I'll start at 4:42. If you want to go over your notes, so if you just stand up and stretch, that's all. Good.
How do you feel?
I like it.
Very
maybe how nearest neighbor is generally in what sort of a situation would you sort of okay, nearest neighbor. I mean, one was like house prices.
Yes, there's a really simple user that's sort of a force that what your data is telling you. So anytime you can represent your data with a vector x, and a new thing comes in, the first thing you'd like to try is, okay, what's the nearest thing in my data set? I'd like to just move it on. With house prices, you know, people actually use nearest neighbor, but they do it in a very special space. It's the GPS space. Right? You know, if I want to sell your house, I see does your neighbor, how much that's sold for. And really what people do is, okay, is that a similar house to yours? And then they just copy over the price. So take an average of your 10. And here we're saying that it doesn't have to be in the 2D Earth coordinate, it can be in any sort of space. Even for training data points. So your data set is just xi. So here, for example, this is sort of the training data. X and y is the y, and you would like to predict what x is at all these points. Yeah. Well, if you're doing one-dimensional regression, if you're doing one-dimensional, but if you're doing multi-dimensional regression, this is categorization, classification. So in classification, you can check the reason why I put this. Is my label Okay. All right, settle down. All right, so there was some confusion, so let's make sure we get this right. This is sort of the simplest function fitting with nearest neighbor, right? You're given sort of 4 data points. Your training data set consists of x equals this value, y equals this value, and so on for those 4 data points. And you are fitting a function. You're searching over the space of all possible mappings from x to y, and you're finding this particular function. And the way you're finding this function is not by explicitly searching, right? You're not writing down the space of all mappings from x to y. You're sort of saying, I will start at this x, I'll find the closest y, and that value I'll copy over. And yes, it will be jumpy because at some point, at this corner point, what's happening is your distance in this x space, in this x coordinate space is identical to this point and this point. So that's why after this it jumps to this one. And so this is an extremely bumpy fit, but it's a nearest neighbor functional fit to the data set. Okay. And we'll make this smoother and better by doing weighted nearest neighbor, for example. That makes sense? Okay. So one concept that we'd like you to know is this concept of sort of this comes up a lot with Voronoi cells. So what I'm showing here is the black dots are the data points that are given to you. This is an x1 and x2, so this is a 2-dimensional input space. The y is not plotted here. And what this figure is showing is every line here. So a point on that line has 2 data points to which it is that are its neighbors with equal distance. So a cell is formed when every point that falls in this cell has this as its closest nearest neighbor, and the boundaries are formed when you have two of these data points that are equidistant. Does that make sense? So the idea of Voronoi diagrams. And what matters in these diagrams is what sort of distance function you use. The most common one that you're all familiar with that we'll use is Euclidean distance. Right? In two-dimensional space, d-dimensional space, we'll use Euclidean distance. What we'd like to introduce to you, you may have seen this before, but we'd like to introduce this idea of scaled Euclidean distances, where you can sort of scale up different dimensions. So here, I've done xi1 minus xj1 squared plus 3 times the other coordinate, right? And what this scaling of a coordinate is going to do is it's going to sort of stretch one dimension out and change the shape of the Voronoi cells that you're going to end up having. Okay? So let's draw a picture of why this might be an interesting thing to do. Let's say this is dimension 1, or x1 if you will, the first coordinate. This is dimension 2, or the second coordinate if you will. And this is a 2-class problem, and I'm going to draw the data. So +1 is one of the classes, it's positive class. And this is how the data is distributed. And -1 is the other class, and this is how that data is distributed. So this is a point in a 2-dimensional space. That's the data set you have. And it should be clear that there's something, so there's a skewing happening in one of the dimensions, right? Let's say you were measuring, this was height, you were measuring in feet. This was weight, you were measuring in milligrams for whatever reason. Right? So the dimensions are off in different scales. And this happens. You go out into the world, some sensors are just measuring in 2 different dynamic ranges. Right? So you end up collecting this data, and one of the dimensions is just off. What happens when you ask for a new point here, you don't know its label, and you look at the neighbors? Right? Because the dimensions are off, it will seem like one of the categories is overrepresented, but that's only because you're measuring distance in a Euclidean distance sense. Right? What I'm drawing, why am I drawing that as a circle? That is a level set. There's a contour level set of the Euclidean distance, or the L2 norm, and we'll write that out. Okay? So it seems like you're seeing a lot of the negative data pop up, and so you'll make a prediction this is negative. That's not right. So what you need to do is adjust your distance. So what you'll do is, if you're writing distance between a vector x and another vector z, and let's say this is, right now this is Euclidean distance, and let's write squared distance for now, x1 minus c1 squared plus x2 squared. You'll say, if you have prior knowledge, you'll say that, but we'll talk about learning this as well. You'll say maybe the distances in the first dimension matter a lot more. So if you're different slightly in the first dimension, it matters a lot more towards the final distance computation than differences in the second dimension. Does that make sense? Right, so this is fixing for the scaling problem that you're having in one of the dimensions. So, and in general, between 2 arbitrary d-dimensional vectors, you can write this as 1 d, some sort of sigma I squared xi minus z. So in every single coordinate from 1 through d, you can have some sort of a scaling factor that corrects for it. Right? And a simple sort of math trick, a linear algebra trick, you can write this as a matrix, sigma 1 squared, sigma 2 squared, sigma d squared, and the zeros on the off diagonals. Can people on that side see that? Okay. So what I've done is this is a diagonal matrix. On the diagonals are sigma 1 squared, sigma 2 squared. On the off diagonal is 0. So there should be a transpose here. This is the difference of x minus z vectors. you know, because all the off diagonals are 0, there are no cross xi with zj, for example. It's just these terms that survive, and that's that. Okay? So this is a special case of a type of distance that people heard of, something called the Mahalanobis distance. One person. Okay. So this is called Mahalanobis distance. And the general form is x minus z transpose A of matrix X is. So instead of having a diagonal matrix, you can have an arbitrary matrix sitting in between. And so this is the distance squared. You sort of take the square root of that and get the Mahalanobis distance. That makes sense? Okay. Anybody know any, like, can I use arbitrary matrices A? Are there any constraints? What type of matrices are allowed? Symmetric. Okay, that's one. It has to be symmetric, otherwise the distance between x and z, you swap the order, you get a different distance. It has to be a metric. Anything else? Yes?
Positive definite.
Positive definite. Why?
I know that variance matrices have been positive, so I was thinking.
Covariance
we wouldn't
matrices are positive definite, yes, but
We would have
so
a negative result on the list.
not bad. Distances would be negative. Distances can only be positive. So if this is metric properties, you have to be symmetric. Triangular inequality, you have to be positive. If we talked about this a little in homework 0. The definition of positive. Let's talk about semi-definite matrices. Is a symmetric matrix where x transpose AX is greater than 0 for all x. Including the non-negative. It doesn't have to be an all 0 vector. No matter what vector you choose, it's always good. And this is sort of a one-to-one mapping. Has to be, you have to have a squared distance or a distance that's positive, otherwise you'll end up with negative distances, imaginary distance. That makes sense? Okay. So what do these things look like? Let's see. So this is what we talked about. I can have this sort of sigma I sitting in here, and it's just sort of scaling each of the coordinates. If you really have a diagonal matrix, then these numbers are essentially scaling the coordinates. These are the level sets of the contour maps. What's happening is this point right here is the origin, that's 0. Every point on a circle is equidistant to the origin, right? So, and the circles are increasingly, distance equals 1, 2, 3, and so on. And what this is showing to you is that if you draw a symmetric, like a circle, this is an ellipse, a circle, this point would be the same distance as this point here. What's happening is that, in L2 sense, this point is closer, but in this squished Mahalanobis sense, this point is the same distance as this one. Right? So it's basically fixing for the scaling that may be going on in the different sensors that you're collecting. And this is an axis-aligned distance. This is sort of not axis aligned, right? Here, there's an arbitrary matrix. It's non-diagonal, and what it's doing is it's also capturing that xi and xj interact. The different axes, the different features or whatever coordinates you are measuring are not really independent or not really that different. That makes sense? Okay, so that was one generalization of Euclidean distance that we did. Let's quickly talk about another generalization. And notice all of this, the distance metric that you choose will change what sort of neighbors that you end up getting, and therefore will change the predictions that you're making. Okay. All right. So Euclidean distance is. Let's just go back to the Euclidean distance. We're talking about. summation of over I from 1 through d of xi minus zi squared, and then you're doing square root. This is an L2 norm of the difference of these two vectors. You can generalize those to these things called Minkowski distances. Where you replace 2 by another number of p, right? And p can go from 1 to infinity, if you will. Right? In this case, you have to replace this by an absolute value. Here's, for example, this is why it tends to be important. If I set p equals 2, I get back the Euclidean distance. If I set p equals 1, I get back something that is known as the Manhattan distance. So I equals 1 through d, absolute value xi minus I, no powers. In 2D coordinates, it feels like the Manhattan distance. Go right for these streets and up for that many streets. So if you're in Manhattan coordinates, you're just sort of summing things up. What do these things look like? Let's say, this is x1, this is sort of dimension 1, this is dimension 2, there's your origin. We'll make our life easier. Instead of looking at distances, we'll talk about norms, so distance to 0. This is the L2 norm. That's the circle, which means every point here has, the x1 squared plus x2 squared square root is equal to, let's say, some radius r, right? Here's your L1 norm. Every point on that diamond has absolute value x1 plus absolute value x2 equal to some value r. Right? So far, so good. P has come down. What happens as P approaches infinity? Limit as P approaches infinity. Any guesses?
Square.
Becomes a square. Why?
Because you, as long as, so for example, if you're going for the top, it would be, you can say, oh, y equals 1, or y equals r in this case. And then as far as you go out to the right, as long as you stay with your exponent less than r, the maximum point is always going to be the y equals r.
Yeah, okay. So the intuition about, sort of max norm is correct. The proof is going to be in the notes that I upload. It's a really simple proof, but I'd like you to look at it. So basically what we're saying is limit p tends to infinity. This thing basically becomes equal to max of I equals 1 through d of xi minus zi. So you just, if you think about this, what's happening is that, and I'll walk you through the proof. It's in the notes. Here's a number. You're raising it to the power p. You're summing it up, and then you're doing a power of 1 over p, right? Let's assume, for sake of simplicity, that one of them is the largest. There's a unique argmax. Pull it out of the summation. Now everything else in the summation is less than 1, because it becomes the max divided by every value divided by the max. It's less than 1, you start raising that to powers of infinity, so anything start approaching 0. So the only term that survives is sort of the largest term. Okay? It's a simple walkthrough. The proof is in the notes. Okay? Here's what that looks like in terms of a picture. This is sort of what it looks like. This is the contour map of the max norm, which means every point on this green line has max of xi, where I can be 1 or 2, equal to r. Right? So this point has, x2 is r here, right? x2 is plus r, x2 is minus r, and x1 varies from plus r to minus r, and the other way around on the other axis. Right? and so sort of this is p equals 1, this p equals 2, this p equals infinity. So power of pattern recognition, what happens is p becomes less than 1. Any yeses? Comes called in.
Yeah.
You get level sets that look like that. Okay. Ultimately, as you approach 0, you get sort of this sort of diamond shape. And 0, anything less than 1 isn't defined as a metric, but you can still sort of look at the normal. Okay. So random foray into sort of abstract math. Why did we do this? We did this because depending upon what your data is measuring, you may want to use different distances. Right? In particular, Mahalanobis distances like the ones that we wrote down here, where there's a matrix sitting here. There is an entire class of methods that's called distance metric learning. And the goal is to how do we learn this matrix that learns the right scaling of our data and also learns what are the correlations so that nearby points come close together and the points that are maybe of different categories go farther apart in the space. So the entire goal is sort of to learn this matrix. And such methods typically improve the performance of vanilla nearest neighbor, which would be Euclidean distance. Okay. So that was these are the level sets, the contour maps of Euclidean and Mahalanobis. These are the level sets on contour maps of Minkowski distances for various values of p. It starts, this is p equals 1, this is p equals 2, and that's your standard Euclidean distance. P equals infinity goes towards like a square box-like looking shape, and as it gets small, it starts to look this concave shape. Okay. And this is sort of the level sets and various things. Okay, one concept that I want to introduce, and this is a word that you might hear as things go on, the difference between parametric and non-parametric models. And I'd like to introduce that specifically at this point because it makes a lot of sense in the context of nearest neighbor methods. So the key question that is often asked that distinguishes between parametric models for machine learning and non-parametric models for machine learning is your hypothesis class growing as you see more data? Let's think about that question for a bit. Let's pop back onto this picture. Remember we told you there's a data set. You choose a hypothesis class. With nearest neighbor, we haven't actually told you what that set is, right? And this is where we're touching that question. Let's say your data was growing. Let's say you didn't have 10 samples or 100 samples. Let's say that was increasing to 1,000, 10,000. Is this set increasing as you get more data? That's the question. If the answer is, yes, then we're working with what are known as non-parametric models. The answer is no, that we are committed to our class of functions, regardless of how much data that we get. That's a parametric. Sorry, did I flip that? Non-parametric. Yes.
Just a quick question. Is it because it's related to how parametric statistics and non-parametric is in terms of normal distributions? Like so, when we say that it is a parametric model, it is because it falls like under the normal curve assumption still holds true, and hence the number doesn't go up that high. Whereas if it is non-parametric, it doesn't really fall under that, and hence the number of possibilities or the sets go up. Like just an intuitive.
The first part of the question I agree with. This is the same thing as parametric statistics versus non-parametric statistics. I'm trying to draw the same comparison. I don't really see the connection with the normal distribution yet, and I want to hold off on the normal yet because we're going to talk about things like that next time. Because we're going into probabilistic classifiers next time. So Okay. So this seems like an abstract thing. Let me make that more concrete. What do I mean? So think about nearest neighbor, and nearest neighbor is the perfect example of a non-parametric method. here's nearest neighbor. Let's say you start off with 2 samples. This is class 1, this is class -1, or the other way around. Doesn't really matter. And you're doing 1 nearest neighbor, right? What is this indicating? It's indicating that every point in this is x1 and x2 two-dimensional space. Every point here, the nearest neighbor ends up being this point. Every point here, the nearest neighbor ends up being that point. So this is the decision boundary or the classification boundary, right? This is what is learned right now. This feels like this is a linear decision boundary, right? So it feels like right now, the hypothesis class that we searched in was linear classifiers, things that draw a straight line between the 2 categories that we're separating. However, as soon as you get another data point, let me draw one more, 4th data point, the decision boundary changes. It's changing because this is the Voronoi cell argument that we were making, right? Basically, every point here, the nearest neighbor is this. Every point here, the nearest neighbor is this. So because now you've seen 4 samples or 3 samples of this one and 1 of this one, the decision boundary became a little more complex. Okay? And as you see more and more data, for example, if I see this, or if I see this, if I see this, as you see more and more data, one nearest neighbor is happy to carve out arbitrarily complex decision boundaries in this space, right? So this is an example of a method or a model where the hypothesis class, or the mapping from X to Y, is becoming more and more complex as you see more and more data. Right? You're not committed to linear classifiers or polynomial classifiers, which we'll see later on, but sort of the class is increasing as you get more data. Does that make sense? Okay, it's fun to play around with this really arbitrary funky shapes. Okay. All right, so nearest neighbors are an example of, does the capacity of the hypothesis go? Yes, it's an example of a non-parametric model, and we have not yet seen a parametric model, and we'll see that next time. All right, so let's look at some other design choices that we made along the way. Here are some of the questions we asked, right? Okay, what distance metric to use? How many neighbors? And is there a weighting function? So we already looked at different sort of distance functions. We know that they can help you with scaling and they can change what happens. Let's look at how many neighbors and do we have to weigh every neighbor equally? So this is what we were. Okay, let's go there. So all neighbors may not be the same. We know that as we increase, so this is a data point. We've seen this picture. If this is one nearest neighbor, as we increase the neighborhood, your proportion may change. This is for classification. Here's that same picture for regression. So this is one nearest neighbor for regression. This is the function that you're fitting. And one nearest neighbor for regression tends to be extremely bumpy. So this is sort of x. And as you see different data points, it sort of climbs up. This is again one nearest neighbor. As you add more nearest neighbors, it gets a little bit better, but it continues to stay bumpy. So what's happening here is it's finding every point here on the x-axis. We find the 9 nearest neighbors, we take their value and we average that uniformly, and we get this sort of a function. Okay? So now let's ask the question, do we have to, when we wrote the definition, do we have to weigh everything equal? And no, you don't. You can sort of, the natural thing to do is to weigh points that are closer to you, higher weight than far away. So let's write that down. Here's the neighborhood set. We said this was k nearest neighbors. Let me do a simple thing. Let's set k equals n. So we're going to look at all possible neighbors, right? The entire data set. What happens to unweighted nearest neighbor in this case? So y hat of x. For regression, we said just, what was that? Mean, exactly. So we were going to average the values in this neighborhood suite, right? if you look at all the neighbors, it doesn't matter which data point you're talking about, you're basically producing the data set average, right? And what that looks like, if we were trying to fit a function, it's just the average value, it's a flat line that you're fitting to that thing, right? So we can't do that. Here's a simple fix, right? Just add a weight here, and instead of dividing by k, so divide by, so add a weighting function, I goes from 1 through n, and I goes from 1 through n of the weights, and just a normalizing. So instead of an unweighted average, this becomes a weighted average. Make sense? This wi is just a number for each data point. That's how much we're listening, for this. Let's be very clear. Let me write this more explicitly. Let me say wi of x. For this data point x, we're going to go to the ith data point and give it weight I. So x is my test point. I'm going to go to I training points, and I'm going to assign them all weights. Okay? And this is the regression prediction. The classification can be y hat of x is, I'm going to just do weighted indicator C 1 to n, and do an R x. Oops. Right. This is extremely similar to the definition we wrote down before. We're just giving each training data point a weight. And what we'd like to do is give things that are close to this test point higher weight and things that are farther from this test point lower weight. Here's a simple way of doing that. This is a one-dimensional space. Let's say this is x, and this is R1, one-dimensional space. Let's say this is x test. So this is W of x, if you will. So this is, I'm just going to use a function like this. If you're close to, maybe this value is 1, the absolute value doesn't really matter, it's the relative height differences and how quickly it falls that matters. If you're absolutely close to the x point, like if I query a point and my data set contains that point exactly, then the distance to this x test is right here, so that weight will be really high. As I go find a neighbor that's really far away from this test point, I stop listening to them, right? So this sort of decays to 0. So really standard simple thing to do. So wi of x is basically equal to e to the negative of some distance between x and x divided by, let's say, some bandwidth. This is extremely reminiscent of the Gaussian distribution. This is not a distribution. There's not a probability here. We're just looking for something that has that shape, right? And so we're looking at squared. Well, there's no squared here. It's just some distance. You measure your distance, and we're going to divide that by a scaling factor, and that's the weight. Okay. So what that will do is when we look at some of these plots. What we'll do is when we look at some of these plots, here's a one nearest neighbor fit. If I'm at this point, I'm going to weigh these two pretty heavily, and these points are all far away. But I'm going to take a weighted average of all these training points to come up with, every time you pick an x, I'm going to come up with a prediction, and I'm going to fit a function like that for every single x value. Right? And I'm going to calculate that weight with the formula that I just gave you. So I'll stop here because we're out of time, but next time what I'll show you is two extreme cases. What we'll do is we'll set the bandwidth to infinity basically, and we'll say that if you do that, it'll collapse to an average of the data set, and we'll set the bandwidth approaching 0, and if you do that, it'll collapse to something else. And somewhere in between is the right thing to do, and that's what we're looking at. Okay, let's stop.